Hi, I'm Ms. Vaughan. Let's have a look at instantaneous rate of change. Recall these three words. That's a secant. A line that passes through to 2 points and it crosses it. And if it doesn't cross it, it's called a chord. And if it's just touching and it has the same gradient as that point, it's called a tangent. We're going to look at tangents of lines. So here we have a parabola. The blue line is a tangent at that point, and this tangent is described as the line that just touches the curve at that point, and it has the same slope or the same gradient of the graph at that point. We can see that the parabola has negative gradient, and then 0, and then slightly positive, very positive. So the gradient changes. So when we draw a tangent, this tangent has the same gradient as exactly that point, not the whole graph, just that point there. Now that's a secant. Why am I drawing a secant? Let's have a look. Do they have the same gradient? No, the tangent has a much better gradient than the secant. So we're going to use the tangent to draw and estimate the gradient at that point. So for the graph y equals x squared minus 2, this parabola here, find this instantaneous rate of change at x equals 1. So we draw that line there at x equals 1. We try to draw it so that it's just touching at that point and has the same gradient. And then now we can find the gradient of the blue line, and therefore that would give us an estimate of the gradient at that point for the parabola. So we can pick 2 points on that blue line. Let's pick 0, minus 3 and 1.50, and we apply the formula y2 minus y1 over x2 minus x1, and we obtain 2. So the instantaneous rate of change at x equals 1 is 2. So instantaneous rate of change. How can we make the secant become more like the tangent to give us a more accurate instantaneous rate of change? So here's a secant. What happens when we move the two dots a little bit closer to each other? We can see that the secant is becoming more and more like the tangent. So here the difference is much bigger than the difference in the blue line that we've drawn, and it's also still bigger than the difference in the 2 dots in the grey line. So we can see that when the difference in x is smaller for the secant, so the line that goes through 2 points, we're getting closer and closer to the tangent. So out of these 3 lines, we can see that the grey one is closest to the real gradient, but we can move the dot even closer, like the black line, and now that line is even closer to the tangent. So the smaller the difference in x, or the difference in the 2 dots, then the more accurate our rate of change is. So we use the secant, but if we make the difference small, it almost becomes the tangent. Let's have a look at instantaneous rate of change by exploring this graph over here. Here we have the graph of a quarter x squared, and I've drawn a secant between the points A and B, and if we found the gradient between the point A and B, so 4, 4 and 2, 1, we can see that the gradient is 3. Now what happens if I draw lines that are between the points that are closer and closer together? So instead of picking A and B, I pick 2 points that are closer and closer. Then I will get the gradient to be closer to the tangent. So let's have a look at what the gradient or the coordinates become when that happens. So between 2 and 3 this time, we can see that the coordinates are 3 and 2.25. You can do this slowly if you want. So for when x is 3, you plug it in here. 3 squared is 9. 9 divided by 4 is 2.25. So I've obtained the x and y value for the domain 2 to 3. So these are all x values, and here I've done the coordinates. Now you can sit here and do the gradients, or just watch and trust me and observe the pattern. So I've done the gradient for the secant, the pink line there between 2 and 3. Then I'm going to figure out the coordinates and the gradient for the line between 2 and 2.1. Now let's notice what happens between 2 and 2.01. So the x value for 2 and the x value 2.01 will give me the y value 1 and 1.010025. So I'd use a calculator for this. The gradient is 1.0025. Let me recap. So I've done 2 points, 2 and 4 up here. I've drawn a straight line, worked out the gradient, it was 3. Then I've done the gradient for the line 2 to 3. So I've drawn a secant from 2 to 3, and I found that the y coordinates were these. The gradient was that, 1.25. Then I repeated that practice, and I did, instead of 2 to 3, I tried 2 and 2.1, the x values, and I found the y values for those 2 points, and I plugged it in and found the gradient to be 1.025. Then I did it again for 2 and 2.01, found the y values, plugged it in to find the gradient, and I'm going to do it one more time for 2.2 and 2.001. So 2 and 2.001, that's my y value, and I can see that the gradient becomes 1.00025. And I can see that the gradient, as my x changes and becomes really close to here, or my line becomes, my secant becomes really close to the tangent, it's closer and closer to 1. Let's try this. Example 2. The weight of a person over a 40-week period is illustrated in the graph below. Estimate the maximum weight and the time which this occurs. So when is this maximum weight? Well, we can see it's here. It's 35 kilos. And it happens, sorry, it is not 35. It's 35 weeks and it is 85 kilos. Estimate the average rate of change of weight between week 10 and 15. So week 10 and week 15. So we find our y values, and then we have to just plug it in as y2 minus y1, x2 minus x1, and we get -1. So in that period of time, we can see that the average rate of change, or the gradient, is -1. See? Negative. Example 3. Estimate the instantaneous rate of change of y with respect to x at the point 5, 127 on the curve y equals 2 plus x cubed by considering the secant PQ, where Q, so this is P and Q is 5.01. Notice the x value, so P is 5 and Q is 5.01, so very close. And if P is, sorry, the y value for Q looks scary, but all I did was put the x value 5.01 into the equation here. Can you see the equation is 2 plus x cubed? So 2 plus, well, x for Q is 5.01, so 5.01 cubed. So when we plug that in, we get 75.1501. Now what happens when we repeat this same gradient for 5.001? So see, we're getting closer to 5. And when we plug it in, we get 75.01. And then if we repeat it again one more time with 5.0001, so the distance between the 2 points is smaller, we can see that we get a gradient that becomes closer and closer to 75. And if you will do the next few chapters, you can work that out, and it is true. The instantaneous rate of change of y with respect to x at x equals 5 is 75. So let me just recap what I did here. So here I have the x value to be 5, and then the next point was 5.01. The y value is calculated by putting 5 into the equation. 2 plus 5 cubed is 127. And the y value for the q point is by putting 5.01 into the equation. So 2 plus 5.01 cubed. And instead of figuring that out, I just did y2 minus y1 and leaving that in that format and letting the calculator evaluate it. So you can see that's y minus y over x